Yes, let's discuss in our 11th lecture about more about quarks, and then later I will also talk about the isotopic spin and its physical significance, though we have already discussed isotopic spin. What we have seen while introducing eightfold way, that mesons and baryons reveal patterns that could not be explained by the known particles like protons, neutrons, and pions. And these inconsistencies led to the proposal of quarks as subatomic constituents, each carrying fractional electric charge. Now, there are six types of quarks: up, down, charm, strange, top, and bottom. They combine to form various baryons, each with distinct properties. We will discuss about the properties of these particles. What I have told you, that the anomalous magnetic moment of baryons and mesons were suggesting us that there is more to these baryons and mesons. They are not showing normal magnetic moment. There is some strange component of the magnetic moment also involved, which fortunately overcame by Gell-Mann and Zweig by proposing quarks inside the hadrons, and that there is a charge distribution inside the hadron. There is these hadrons have got a structure, there is some distribution, and because of that these magnetic moments are not normal. Even, for example, neutron has got the magnetic moment. We shall try in one of the classes to obtain the magnetic moment of the neutron, proton, and other particles using the quark wave functions. Now, the postulation of quarks offered a solution explaining those anomalies by considering the intrinsic magnetic moments of quarks within the hadrons. Now, let us start with what we have noticed, that the nucleons, lambda, sigma, and cascade constituted a natural group within the baryon family, all having spin half and parity positive, and the mass vary from 940 MeV for the nucleon to 1320 MeV for the cascade. Remember this pattern, proton, and we have cascade here. Therefore, it is difficult to argue that they are different states of one particle. It was true when we were talking about proton and neutron as a member of isodoublet. Or pi plus, pi 0, and pi minus as the member of isotriplet, because when the electromagnetic interaction was switched off, then the masses of these particles found out to be exactly the same. But when we are talking about these octets of the particles, what we are realizing that mass of the proton is 940 MeV, while mass of cascade is 1320 MeV. In 1950s, it was tempting to regard these 8 baryons as super multiplet, and they belong to the same representation of some enlarged symmetry group in which SU2 of isospin could be incorporated as a subgroup. This SU2 of isospin, which was introduced in our earlier class, this was a special unitary group in 2 dimensions and with determinant equal to 1. And here this was extended to SU3. What Gell-Mann argued, that the larger symmetric group is SU3 and the octet constitutes 8-dimensional representation of SU3. The decuplet is a 10-dimensional representation, etc. Notably, the difference was that we had proton-neutron K plus K0 or cascade 0, cascade minus, that fell into fundamental representation of SU2, whereas in SU3 this was not true. This rule was reserved for quarks U, D and S, which form a three-dimensional representation of SU3, which we have discussed in the earlier class. With the necessity of charm quark to understand the branching ratio of KL0, this was decaying to mu plus mu minus. This branching ratio turned out to be smaller than 10 power minus 8. That is the what is KL0 made up of? D and S bar quark. So, and D's quark, charge of D quark is minus 1 by 3. Charge of S bar is plus 1 by 3. Therefore, this is a neutral particle. Therefore, the interaction would take place via Z0 exchange, and Z0 then giving rise to mu plus mu minus. This was found to be almost not an observed process, while people had observed K plus decaying into mu plus nu mu, while K plus is a particle which is made up of U and anti-strange quark. Therefore, people had observed K plus decaying into mu plus nu mu, while there was no evidence for KL0 decaying into mu plus mu minus. This neutral exchange was not observed, and this is known as in the literature as flavor changing neutral current. They were not observed. D to S bar, as you can see that this change in the neutral current interaction, this was not observed. And later, with the discovery of J by psi meson, the flavor symmetry group of strong interactions was extended to SU4. Therefore, the explanation why we don't have KL0 going to mu plus mu minus, and while we have K plus going to mu plus mu, and later the discovery of J by psi meson, we were knowing that actually there are not 3 quarks, but there are actually 4 quarks, up, down, charm and strange. And then later people observed bottom baryons and bottom mesons. Therefore, bottom quark was introduced, and finally top quark was predicted, which was later observed in the experiment. Therefore, there were 6 quarks. Therefore, the things which started with SU3 with U, D and S, with the introduction of charm quark, was extended to SU4, and then finally with the top quark it was extended to SU6. However, it may be noticed that isospin SU2 is a very good symmetry, as the particles falling in this multiplet differ in mass only by a few %, which is understood as the contributions from the electromagnetic interaction is switched off. Whether you talk about UD, you talk about proton-neutron, you talk about K plus K0, or you talk about any other particle like cascade 0 and cascade minus. Whereas the eightfold way is a broadly broken symmetry, as we have discussed that mass of the cascade baryon is much larger than the mass of the nucleon. This mass difference is about 40%. Nevertheless, it is regarded as a fair symmetry, as mass of the strange quark for the UDS is almost close to the mass of the U and D quarks. The situation becomes really bad when one considers charm baryon like lambda C plus, which consists of a U quark, D quark and a charm quark, which is twice more massive than a lambda, which is made up of U, D and S quark, though they belong to the same super multiplet SU4. Therefore, the masses here, as you can see, they are really becoming quite different. In the 1960s, as we had told, that Murray, Gell-Mann and Zwick independently proposed the quark model to explain hadron behavior. Gell-Mann named them as quarks and Zwick called them as asses. experimental evidences much later, which is a much later development. Therefore, phenomenologically it was first predicted. Then experimentally it was observed much later in the high energy accelerator experiments which were the results which were quite similar to what we had in the case of Rutherford alpha particle scattering experiments, where we had large angular scattering, which I had discussed in my very first class. Like here also we have structure of the proton, which was obvious from the scattering of electron with the proton target at high momentum transfer square. It was found that there is a large angular scattering which was telling us that there is something inside the proton. To summarize, we have 6 quarks. Corresponding to them, we have 6 anti-quarks, and these are the charges of the quarks. These are the masses. These 2.16, 4.67, these are the current quark masses. These are the models which predict the quarks in the free state. Then we have the limit on the mass of the top quark which has been observed, which is around 173 GeV. And then we have anti-U, anti-D, anti-S, and similarly 6 anti-quarks. Therefore, we have 6 quarks and 6 anti-quarks, and this is how we talk about the quarks inside the hadrons. And then these are assigned quantum numbers, which we call by the name up quantum number, which is +1 for the U quark, down quantum number, which is -1 for the D quark. Strangeness quantum number, which we have discussed, is -1 for the strange quark. For all the others, 0. Charmness quantum number is +1 for the charm quark. Bottomness quantum number is -1 for the bottom quark, and topness quantum number is +1 for the top quark. Now, if we talk about anti-top, then topness quantum number is -1. If we talk about anti-U, then the upness quantum number is -1. And all of these quarks, they are assigned baryon number to be 1/3. All of them are assigned baryon number to be 1/3. All these particles are spin half fermions. All these particles are spin half fermions that we have to remember. Now let us go back to the discussion on isotopic spin, and what I had told you that isotopic spin was introduced while looking at proton and neutron. The masses of when the masses and binding energy of some of the nuclei were observed, which differed only in one proton and one neutron, then an essential concept when we talk about isospin is that the matrix element for a particular interaction, which is related to the cross section. If you recall the Fermi's golden rule, then the decay rate is proportional to the matrix element square. The cross section is also proportional to the matrix element square. Now, if we believe in isotopic spin algebra, if we believe that really it guides us, then using this isotopic spin, we can predict the cross sections of various other processes without measuring them. And then when we measure them, it was found that really they are in agreement with the theoretically predicted values. This is what we are going to talk about. Now, suppose we are talking about an initial state and final state. The initial state wave function is being represented by psi I, and the final state wave function is being represented by psi f. Then the matrix element, this is how we are going to represent it, where A is the isospin operator, which only depends on the total isospin, and the cross section will be proportional to the transition matrix element square. Now, if we are talking about the initial and final state to be isotopic half spin state, then the amplitude will be A half. Or if we are talking about initial and final state to be purely isotopic 3 half state, like for example, just I am talking about pi plus p going to pi plus p. We know that pion is isotriplet with I is 1 and I3 is plus 1, while proton has I is equal to 1 and I3 is plus half. Therefore, plus 1 and plus half projections are algebraically added will give us plus 3 by 2. Therefore, for A equal to 3 by 2, for initial and final state of I equal to 3 by 2, the cross section is proportional to this transition matrix element square. Now, if the strong interaction treats all total isospin I particles the same, we need only to specify the parameter mi for each total isospin in order to complete the calculation of relative cross section. One of the simplest cross section calculation is nucleon pion scattering. For example, I have here taken the various example of pion nucleon scattering, where you have a pi plus p and a pi plus p in the initial and final state. Similarly, you have a pi 0p and pi 0p in the initial final state. And then as we have moved on, we have pi plus n and pi 0p. We have pi minus p and pi 0n. Therefore, there are various processes. Now, in general, it is difficult to accelerate a neutral particle. Therefore, we don't use pi 0 beam. Then a free neutron target, since it has got a certain lifetime of 890 seconds, therefore people don't take or can't take any free neutron target. Always the experiments are either done on proton target or deuterium target. Deuterium has one proton and one neutron, and then we subtract the results from the proton to get the results on the neutron. Therefore, truly speaking, most of the time we talk about pi plus p going to pi plus p scattering, then pi minus p going to pi minus p scattering, and pi minus p going to pi 0n scattering processes. These are the processes where we can accelerate a pi plus or a pi minus. Now, if you believe in isotopic spin algebra, then you can see that we have pi plus and proton. Pi plus has isotopic spin 1, whose projection is plus 1. Proton has isotopic spin half, whose projection is plus half. Now, projections are algebraically added. Therefore, we have plus 1 and plus half to give you plus 3 by 2. And plus 3 by 2 you can only achieve when I will be 3 by 2, because in general 1 and half can give you half also, besides it giving you 3 by 2. But 3 by 2 can have a projection plus 3 by 2, while half cannot have a projection plus 3 by 2. Half can only have projection plus half or minus half. Therefore, the final state is 3 by 2 plus 3 by 2. And this guy is known as Clebsch-Gordon coefficients, which you can find out in PDG, or you can type on Google, see PDG values. You will find that you can find in any quantum mechanics book the value of Clebsch-Gordon coefficients. You will find that this value turns out to be equal to 1. Therefore, pi plus p will be represented by 3 by 2 plus 3 by 2 only. This factor will be equal to 1. Now, similarly, if I talk about pi 0p, then pi 0 is one isotopic spin whose projection is 0, and proton is half whose projection is plus half. Now you see, 1 and half can combine to give 3 by 2, 1 and half can combine to give 1 by 2. 3 by 2 can have 4 possible projections, plus 3 by 2, plus half, and minus 3 by 2. Half can have 2 possible projections, plus half and minus half. While we need plus half, then that means plus half I can obtain from 3 by 2 also and from half also. Therefore, here what I have written as 1 half 3 by 2, 0 plus half, and 1 half half, because this is the possibility. 1 half half is also can give me plus half. Now this is again from the Clebsch-Gordon value. This will turn out to be root 2 by 3, and this will turn out to be from the table, if you will see, as minus 1 by root 3. Therefore, for pi 0p, we can write with Clebsch-Gordon C. I may call it as C1, I may call it as C2, and besides they are representing a combined isotopic spin state, I equal to 3 by 2 and I3 is equal to plus half, and here I equal to half and I3 is equal to plus half. Similarly, when I talk about pi minus p, then pi minus p has isotopic spin 1 minus 1 for pi minus. For proton, this is half plus half. Therefore, minus 1 plus half can give me minus half. Again, minus half we can achieve from 3 by 2 I, because its projection will be plus 3 by 2 plus half and minus 3 by 2. And I can also achieve from half. Therefore, as you can see, here also you have two terms. Similarly, you can work out with pi plus n. Therefore, this is how we have written the different coefficients, and these are known as Clebsch-Gordon coefficients. Now, I have written it, demonstrated it for all the reactions for which we should get these values. Now, if you write the matrix element, then as you can see that if I have pi minus n, then pi minus has 1 minus 1, n has half minus half. Therefore, minus 1 minus half, algebraically when you will add them up, you will get minus 3 by 2. And minus 3 by 2 you can only get when you will have 3 by 2 as the total isotopic spin. Therefore, there will be only one term that will contribute to it. And that is why for both pi plus p and pi minus p n going to pi minus n, I am writing the matrix element or the amplitude with 3 by 2. While for the others, I have these terms which are getting represented by Clebsch-Gordon coefficients. Now, if I take the ratio of the cross sections, which will be the square of the matrix elements, and we assume that there is isotopic spin 3/2 dominance. 3/2 dominance means I will ignore this contribution as well as I will ignore the second contribution for pi minus p going to pi 0 n, and take the ratio of the cross sections like sigma plus p going to sigma plus p. The contribution will come from here. Sigma minus p going to pi minus p going to pi minus p. The contribution will come from this part with a factor of 1 by 3. And for this part, the factor will be 2 by 3 because this will be matrix element square. Therefore, you have 1 by 3 and 2 by 3. In principle, if I multiply, this is at the level of the cross sections. Therefore, this ratio for the square, this will be 9:1:2. And experimentally, that means if you take the ratio of pi plus p going to pi plus p upon pi minus p going to pi minus p plus pi minus p going to pi 0 n. That means I am including both 2 plus 1, that is 3. And here in the numerator we have 9. 9 upon 3 means that will be 3. That means if I take this ratio and go to the experiment and measure that, how much is that ratio? That means pi plus p going to pi plus p should be 3 times the sum of the cross sections for pi minus p going to pi minus p and pi minus p going to pi 0 n, if we believe that there is 3/2 isotopic spin dominance. And as you can see from this result, that this is the dashed line shows the results of the cross section for pi minus p. In the final state, we can have a pi minus p or a pi 0 n. And here, this is the result for pi plus p scattering. And as you can see, this number is around approaching 70 and this number is approaching 200. Therefore, this is 3 times the cross sections of what we are getting from pi minus p. Therefore, we say that in pion-nucleon scattering, there is a dominance of isotopic spin 3/2 component. Similarly, if we look at deltas, we know that delta plus plus decays to pi plus p. Delta plus has two possible decay modes, pi 0p or pi plus n. Similarly, delta 0 can decay to n pi 0 or it can decay to p plus pi minus, and delta minus will decay all the time to n pi minus. Now delta plus plus is decaying into pi plus p. Pi plus p is 1 plus 1, half plus half. Delta plus plus is 3 by 2 plus 3 by 2. Therefore, if you again combine this, I have 1 plus 1, half plus half, giving me 3 by 2 plus 3 by 2. Therefore, the method which we have adopted in the previous case, if I follow the same method and try to get the decay rates for these 6 processes, what you will find out that this also represents, as you can see, 1 minus 1, half minus half. That means only what we have, 1 minus 1, half minus half. This can be only achieved since this is minus 3 by 2 with 3 by 2. Therefore, we have 3 ratio. This is 3. These numbers are 3 for delta plus plus and delta minus, while from the Clebsch-Gordon, these values are different. And experimentally, it has been found that this delta, which is isospin 3/2, these processes is pure isotopic spin 3/2 processes, and these results have been experimentally observed. This is not only true here, but even if you take, for example, kaon scattering on the proton, you talk about k minus scattering on the proton, or where you can have pi 0 and a sigma 0 in the final state, or pi minus sigma plus in the final state, or k0 bar scattering on the proton, you will see that we apply the same isotopic spin algebra. We have the cross-section ratio to be this, and it has been experimentally found out to be true. And if you take about the case proton-proton going to pi plus deuteron, or proton-neutron going to pi 0 plus deuteron, or you take the case neutron-neutron going to pi minus deuteron. If you take these cases, then what we know that deuteron is an isosinglet. Why this is an isosinglet? Because deuteron is a proton-neutron bond system. Why we are calling it to be an isosinglet? Because we don't have in nature diproton system or dineutron system. That is prohibited by Pauli's exclusion principle. No two identical fermions can have all the quantum numbers same, while we know that spin of the deuteron is 1. Therefore, we cannot violate Pauli's exclusion principle, and in nature, no one has found diproton and or dineutron system. Therefore, had there been the diproton dineutron system, then we could have talked about I equal to 1 for the deuteron. But since we don't have diproton dineutron system, therefore for deuteron isotopic spin is 0. And pion, we know that this for pi plus isotopic spin is 1 plus 1, for pi 0 it is 1 0, and for pi minus it is 1 minus 1, and deuteron is 0. Therefore, when you will combine this, you are getting 1 plus 1, 1 0, 1 minus 1 on the right hand side. And what is proton? A system with half plus half. Neutron, a system with half minus half. Therefore, if you want to get a system with 1 plus 1, or a system with 1 0, or a system with 1 minus 1, you can see that for this process, if you apply the isotopic spin algebra, then again you can write these processes in the form of what I have told you earlier, and you will find out that if you say two protons you are talking about, or two neutrons you are talking about, or a proton or neutron you are talking about, you can find out that with this, for this pp going to pi plus d, or pn going to pi 0d, or nn going to pi minus d, if you believe in isotopic spin algebra, you can work it out, take it as a homework, and predict the cross section of for these three particles just on the basis of isotopic spin algebra, and you will find that the results are completely in agreement with the theoretical predictions. Therefore, to summarize, we have fundamental particles for both fermions and bosons. Now, there is a difference. In fermions, we have quarks and leptons, while in bosons, we have Higgs particle and the mediating quanta. All mediating quanta are bosons and the Higgs particles. Therefore, the journey which we had started with, the molecules to atoms, to protons, neutrons, to quarks, then what we have seen that these quarks are the building blocks of the hadrons. We will see in the later classes that gluons also play very important role in obtaining the properties of the protons. But before that, from the next class, I am going to introduce symmetry, the role of symmetry in particle physics. Particularly, I will talk about discrete symmetries, where we will discuss about charge conjugation, parity, time reversal, CP, all these quantum numbers, and then we shall obtain the properties associated with the particles if we believe in these discrete quantum numbers. Thank you.